Here's an example of some serious pathology. Here's looking at the normal slice, and then compare that to this slice. There's certainly something different about this. Here we see reddened brownish areas that represent a hemorrhage that started in the thalamus, spread out into other regions of the brain called the basal ganglia, and then spread into the ventricles. So that's all blood. That happened to someone who had high blood pressure that was untreated. And eventually blood vessels in the wall of those little arteries deep in the brain weakened, and blood came out and caused paralysis and loss of feeling on one side of the body. And of course, this person, as you can imagine, did not survive that injury. Something like this can happen with a severe head injury, where someone's on a bicycle, falls off, or on a motorcycle, falls off, and isn't wearing a helmet. And that the impact against the skull and a fracture of the skull can lead to hemorrhages in the brain as well. Let's look at another kind of pathology. So now I'm going to take a slice of the brain in this direction, from top to bottom, or coronally. And so I'll pull that slice out from right about here. And what we see here is the cortex, where all the neurons live. They're about 100,000 for every cubic millimeter, meaning that we have tens of billions of neurons within the brain in different regions. And this is kind of an area that represents the leg. This is an area that represents the arm for movement. We see here a little bit of the brainstem. Look how nice and smooth and well-formed this is. Compare that to the brain here, where a person suffered a brain tumor called a glioblastoma, a primary tumor of the brain. And you can see now that instead of this nice, smooth, glistening tan surface, what we have here are regions of hemorrhage, breakdown of tissue, and this is tumor all in here, not only on the left side of the brain, but as well traveling across to the other side of the brain. And this person, of course, eventually died as more and more of the brain was filled with tumor. There are treatments for this now that are better than at the time this happened many years ago. But this is still an area of great study, trying to prevent and manage brain tumors. One of the things you notice is all these gyri, or foldings, in the brain. Let's compare that to the brain of a rat. Look how small that brain is compared to the human brain. In fact, a mouse brain and a rat brain is just a little bit bigger than a mouse brain, is 1,000th the size of the human brain. So we see how smooth the surface of the right and left side of the brain is in the rodent. It has a very large cerebellum in comparison to the rest of the brain because it doesn't have much frontal lobe. And if we turn the brain over, we can see here the brain stem and the spinal cord. We also see these little areas in here that are for smell. There's a lot of brain in the rodent that's all about smell, because rodents don't use their eyes and ears nearly as much as they use smell to help find their young, get around, look for danger, and find food. So there's been an enormous evolution of complexity in the brain between the rodent and the human brain. Now, how is it that we make a movement, like reaching for a cup or walking? I mean, these are some things that we take into everyday account, pay no attention to, unless, of course, we become disabled and it's more difficult to use an arm or a leg. Well, think about reaching to grasp for an item. Your brain already knows something about the weight of that item, the shape of that item, and the context of where that item appears in your life. For example, if I held up a ball and you went to reach for that ball, you would recognize it perhaps as a ball because it looked like a hard ball that you'd seen before. you would have some idea of the weight of that ball. And so your hand, as it reached for that ball, not only would pre-shape the shape of that ball without you ever thinking about it, but it would be prepared for the weight of that ball. So you can imagine then that in the nervous system, we might see the object, and that information goes back into our occipital lobe to give us a sense of the shape and color. But that information has to be distributed to other parts of the nervous system, to the centers for movement, to the centers for recognition of what the item is, for the centers of our past experience about such items, before we actually go ahead and reach for it safely. We do this thousands and thousands of times a day, reaching for common or uncommon objects. This is a high-level function of the brain. How is it that we walk without really thinking about it? I mean, our legs go moving, our arms might swing as our legs move, but we can walk distances and talk to other people or even do other activities. We can increase our walking speed so that we're running, and we can even run around objects or on uneven surfaces. Well, this takes a tremendous amount of brain activity. The idea of walking is sort of conducted by the cortex, the movement areas of the brain up in those frontal lobes and parietal lobes. And they sort of say to lower centers that can make automatic or flexion extension movements that we might think about as stepping, to do that based on structures that are deeper in the brain that can do that automatic flexion and extension. But if we are on uneven ground, the brain has to work a little harder and capture information from our senses, carry them to our muscles, get that information up to the brain so that we can adjust our movements so that we don't fall or twist an ankle. On the other hand, if you're a basketball player and you're running down the court and you want to pull up and take a jump shot, now we're talking about combining our vision, space, and what people are doing around us, trying to keep us from taking that shot, movements of the arm that have been highly practiced to try to throw the ball in the basket, but also running, stopping, jumping. Highly difficult activities that take lots of practice and become major skills. So in a sense then, what we can say is that we have certain basic automatic movements that even a baby can make, but it takes time and practice and maturity of the nervous system to be able to turn those into the kinds of skillful movements that we bring into our daily life.